Okay, so let's start new topics. We already learned the quantum gates, but here I want to digress a little bit to recall some concept about transformation of matrix or transformation of bases, right? So just recall what we learned earlier, and then you will understand what I'm trying to do. We have learned, for example, we are originally in an O basis, and this O basis has this basis vector. What does it mean when I write I? Does it mean it only has a I basis vector? Does it mean it's one-dimensional?
Set of basis vectors.
I label a set of basis vectors, I label it as I, right? Very good. So maybe this can be I equals to 0, 1, all the way to n, right? Of course, you can argue with me if you really want. Say, oh, you only give me I, you did not talk about this, then it's just 1D. That you are obviously right? But the common sense in math or in this area is that when I write I, it means a set of basis vector, okay? So this is the O basis, and we discussed earlier about the transformation, right? Or instead of thinking about transformation, at this moment, just say that we do have another set of bases or coordinates, and we are going to call it I dash, right? Where I dash again equal to 0. I need to say 0 dash, okay? Yeah, I call it I dash. So instead of calling it dash, I just say I equal to 0, 1, all the way to n minus 1, right? So you understand I dash means n minus 1 dash, for example. Okay, make sense? I have two different systems, right? So we also mentioned that we can create a matrix M equals to I dash J. Well, this can be confusing if you did not study or you did not understand what I said earlier. First of all, what is the meaning when I have this parenthesis and I dash J? Is this a number, a vector, or a matrix? It's a matrix. So in a matrix, how many elements do you have? N by n depends on dimension, but at least you know is some row times some columns, right? Then why I put ij? What does it mean when I say this? Thank you. I've row and jth column elements, right? I just say that the ith row and jth column element equals to what? Equals to the ith basis vector of the new basis inner product with the jth basis vector of the old basis. If this is not clear, then let me spell it out. This is 0 dash 0, 0 dash 1, 0 dash n minus 1, 1 dash 0, 1 dash 1, 1 dash n minus 1, and keep going. N minus 1 dash 0, n minus 1 dash 1, all the way to what? What is the last element? N minus 1 dash n minus 1, because this is the nth minus 1th row and nth minus 1 column, right? Any questions? Right? This is just a simplification, an easy way to write this matrix. Basically, I just think that, of course, to be more formal, I actually should say M, I, J equals to I dash bra inner product with J cat, right? Okay, so that was the matrix we formed. Any questions? Remember this? And then we say, okay, so in the O basis, for example, there is a transformation. Maybe I have a vector that is called psi, and I call it O I represent in the O basis. I do another rotation, right? Or another transformation in the O basis. I also call it UO. It becomes a new vector, phi O. Right? Do you understand what I'm saying here? Is this a vector or a matrix, psi O? It's a vector, I write it as a cat form, right? So this is a vector. And then you multiply with U. What is U? Do you guess? Is a number, matrix, or vector? Yeah, it cannot be a vector, maybe a number, but for the purpose here, I already told you it's a matrix, it's an operation, right? For example, now I rotate myself by 90 degrees. Then it becomes a new vector, phi O. Nothing special, right? Vector multiplies with matrix and then becomes a vector, right? That's okay? Okay. Now, you are looking at my rotation in this classroom. You describe this rotation as this. Someone is riding a bus outside San Fernando, and he or she also see that I'm rotating, but he or she is on another frame. He or she cannot just say that I saw Hiu-Yung rotated by 90 degrees. Right? He probably would say he's spinning indeed, kind of not really rotating because the bus is also moving forward, right? So you see that actually I'm also going backward while I'm rotating, right? To describe this in this new frame, in the new basis, my initial state can be described as maybe psi nu. Okay? And in this process, to describe my rotation or what I have done, you probably need to use a new matrix, U nu. And then you get this phi nu. Is that okay? This is the scenario. The same physical object doing something due to transformation from psi to phi. And if you are at two different frames, two different coordinates, you will describe this same action differently. Make sense? Right? Easier way to, even easier to think about this. How about this? I walk forward one step, and he would say that I walk one step towards him. But if there's another person just walking at the same speed as me, that person will say I want to do some transfer. Let's say that person was walking opposite from me. Then that person will say I'm walking 2 steps in front or behind him, right? So it is the same object, but this U for him is 1 step towards him. For the other person is 2 steps to the back of that guy. Make sense? Right? So that is the U, right? And so you have these two. But we did learn something. We learned earlier that the relationship between this O vector to the new vector is what? I mean, the O basis to the new basis. How do you describe this O basis vector in the new basis? Do you remember? Forgot? Then why do I record this matrix? It's equal to m times this O basis, right? Vector in O basis. This is what we learned earlier, remember? We talked about the rotation of the vector on the 2D plane, and then we come up with this M matrix, right? And then you just need to apply this M to this, then you will get this one, right? And similarly, of course, we also have the final state, phi, O. How is it related to the final state of nu in the new basis? M still, right? Because this is talking about, I try to describe the vector in two different bases. The vector is still the same. Physically, they are the same state. I just look at different direction, right? So this O times M equal to nu, right? So the question here is, what is the relationship between UO and U nu, right? So now we know how to, if I give you an O basis, you already know how to describe a vector. To describe it in the new basis, you just need to multiply the O vector by capital M. But how about if I know that this is called rotation by 90 degrees with a matrix, then what is the description in the new basis? It's just like that, you already know that I'm walking one step towards him, then the guy actually going this direction by another one step. How is he going to describe my action that will result in 2 steps behind him in 1 second? Is that a little bit confusing? The background still confusing? Huh? Who just say something? Make sense?
Offset of something.
Uh-huh. Not really. Okay, so let me describe one more time. So, yeah. I'm just trying to give the background, right? So I think we need to have an example. So for example, if this is O basis, what is the meaning of O basis? For example, let's say the O basis is a stationary. Let's say it is stationary. Okay, this is a stationary basis. You stand there, right? And now I have a vector. Okay, this vector in the O basis is just saying that maybe it is moving at velocity equal to 1 meter per second. That's the state of the particle, 1 meter per second. Is that okay? Is this clear? Just this room, a particle moving at 1 meter per second, right? That is psi. Now, then let's say you stop it. My example may not be that good. You stop it. This is just like the operation in the O basis. You stop it. You do something, right? Some transformation to it. So it stopped. And then the new state, what is the new state when it stopped? I mean, in the O basis, what is the new state? Phi O. What is that? You stop it. Huh? 0, you stop it, right? So the vector becomes 0 meter per second. Although there's some direction problem, just take it for. This is a physical process, right? Something moving at 1 meter per second, I stop it. So the state of the system of that particle change, right? And it's described by initial state, 1 meter per second, and then an action, you stop it. So this is not a good example. You cannot do multiplication. It's not linear. And then it becomes the final state, 0 meter per second, right? So this is O basis. Yeah, we want to correlate the relationship between O basis and new basis. Yeah, and that's what I'm saying. That is that, right? But some of us still get confused what I'm talking about. Yeah. So now, if I have a new basis, new means that just another the second basis. Someone is moving at 1 meter per second. Someone is moving at 1 meter per second. Then in the new basis, that ball was moving at 1 meter per second, right, in this room. But someone is also moving at 1 meter per second in the frame of that person. How is he going to describe that ball? What's the state of the ball for him? Yeah, he will just say V equal to 0 meter per second, right? Now, still the same physics, it got stopped, but probably it is not stopped this time. You actually accelerate. Oh, okay. And then in the O basis, it got stopped, right? Then what is the state of the particle to the second person now? Exactly. It becomes negative 1 meter per second, right? Then how are you going to describe the action? It goes from 0 to negative 1 meter per second. Well, something accelerate. You won't say it gets stopped, right? You say, hey, someone just hit the ball. Am I right? So then I have hit. Or maybe let's just say accelerate. This action is the new operation. So I think you need to watch the video to know what I'm writing, right? But do you get it? So for the same physical process, in the O basis, the stationary frame, you say that it was moving at 1 meter per second, there's operation to stop it, and then it stopped. But in the new basis who is running at 1 meter per second, he says that the ball was stationary and someone accelerates, then you go backward. Right? And the question now is, you were able to describe in the O basis, V equal the initial state is 1 meter per second. The final state is 0 meters per second. The operation is you stop the ball. How do you describe this same physical process from the person who is moving at 1 meter per second? So then you use this matrix such that you will get description is initially it was stationary, someone accelerate it, and you go backward by 1 meter per second. But this is just an analogy. And how you describe it? Now this is what I'm trying to say. O basis stationary, you were at 1 meter per second, stop it, it becomes 0. In the new basis, it was just like stationary, you accelerate it, it becomes negative 1 meter per 0. And how do I correlate this stopping, 1 meter per second to 0 in the new basis? You just multiply by this M matrix. This matrix correlates the relationship between the state. This is just analogy. Right? You need to go through very careful matrix. I don't know if you can do that, but assume you can, then you will find that the state with 1 meter per second times M will give me 0 meter per second. The say of 0 meter per second times m will give me negative 1 meter per second. And now the question is, stop it. Let's say we can quantify it. How do we know that it becomes accelerated in the second frame? Right? So that is what I'm trying to ask. What is the relationship between stop it and accelerate it? Something like that. Okay? Maybe it's still confusing, but think about that. Okay, so I'm going to say that the result is U nu equals to M U O M dagger. So what is M dagger? What's the meaning of dagger? Adjoint matrix. Adjoint, yeah. So what is that? How do you operate it? How do you get it from M? Transpose, compressed conjugate. Very good, thank you. So I'm going to prove it. This is a way to improve our understanding of the math. So first of all, I know psi nu, no. Phi nu equals to U nu, right? Phi nu, psi nu. This is just given, of course, the initial state and the new basis times the operation give me the final state of the new basis, right? This is given, right? Okay, then what I'm going to do is this. I'm going to multiply U nu to the left. And of course, if I multiply, what am I doing? Something wrong. I think I have a typo. I'm not multiplying mu nu. I'm sorry for that. Right? I keep the left hand side the same, but now I substitute. Yeah, so I just copied the wrong thing. Let me do it again. Sorry. Okay, let me just re-say it. I know phi nu equals to m times psi. Wow, it's just completely messed up. Phi O. Okay, so what I'm trying to say is the final state here, right? The phi O is connected to the phi nu by m. Right? So that's why at phi O times m equal to phi nu. Is this okay? Right? But then what is phi nu? Phi nu is just equals to U nu times psi nu, right? So let me just remind you, maybe this is confusing. Phi is the initial state, right? And psi is the initial state. Phi is the final state. Okay, so you see that this is the final state. Final state equal to the operation times the initial state. Is that okay? Right, so similarly here, I'm going to do the same thing for the O. It is UO times psi O, right? So phi O equals to UO times psi O, because final state equal to the operation times the initial state, right? But here I express in the O basis, here expressed in the new basis. And therefore, U nu times m psi O. The reason here is that, again, m connects the old basis to the new basis. So the psi new becomes m psi O. Right? They are both the initial state. Okay? Equals to m UO psi O. Now with this, because you have psi O on the right, and for any psi O this is correct, then it means that U nu M equals to M U O, right? Because this is true for any psi O, right? So no matter, so I have a matrix here multiplied by any psi O equal to this matrix multiplied by any psi O. Then it means this matrix must be the same, right? So let me ask you again. Psi O is what? Is a vector, number, or matrix? Vector, right? M is matrix U. So matrix times matrix still matrix, right? So this matrix times a vector equals to another matrix times that vector. And this, I did not say which vector, it can be any vector in the space. So it's always true, then it means these two matrices must be the same. Make sense? With this, then I have U nu M M dagger equals to M U O M dagger. Okay, I just apply M dagger to the right. So this equal to then U nu equal to M U O M dagger. If M M dagger equal to I, what does it mean? M M dagger equal to I. Very good. It means if it is unitary. But for all the transformation we have, we require it to be what? Unitary, right? Because we need to preserve the inner product. If this is not an unitary transformation, we don't care in quantum computing because it doesn't care, but doesn't preserve the inner product, right? So here I prove this. Now we actually spend a lot of time on this. Maybe you get confused, but after all, it is like this. We earlier, so you can go back to think about that again, but the summary is this. You can describe the same physical process in different frame. I hope you agree with that. An old basis and new basis. So in the old basis, you will see a vector, right? You see completely differently if you are in the different basis, just like the particle case. Stationary one, see that it is moving at 1 meter per second. The moving frame, see that it is stationary, right? So how do you relate the old basis vector to the new basis vector? You use M, this transformation matrix we learned earlier. M times the old vector give you the new vector representation. And then we also want to know, okay, if you do something to that vector, right, operation, how do I describe that operation? Obviously, if we are in different frame, this operation will be different, perceived by different people, right? Like the particle case, I was stationary. I would say, you stop the particle. But then for those who is moving, you will say you kick the particle so it move, right? So how do we relate them? Turn out to be M times the OU times M dagger. There's something called similarity transformation. It's just purely linear algebra. You use it a lot. If you have studied solid state physics, you learn this, you play with this also for the stress in the crystal. So if you really cannot understand, not really a big deal, but you need to have these two equations. And you need to be very clear how to use it. This is in old basis, this is in new basis. right? But I really hope you can understand the proof and also the background, because each piece is composed by some fundamental knowledge you have learned. If you really understand, then you are pretty good with the previous materials. Okay, any questions? Okay, then you can use this to do something, right? All right, so let's move forward. I want to discuss the concept of trace, which should be very simple and you should know. For any matrix A, I will write it as A00, A01, all the way to A0, n minus 1, A10, A11, all the way to A1, n minus 1, right? And then what is the last one? The last row, first column. What do you call it? An minus 1, 0, thank you. An minus 2, 0, right? All the way to an minus 1, an minus 1. I know it is easy for some of you, but it's good to make sure. And I just want to, and of course I can always say this is equal to aij. Basically, it's saying that the ith row, jth column has an element aij, right? So what is the meaning of trace of A? I think some of you already know. What's the meaning of trace of A, of a matrix? Sum of the diagonal elements, okay? This is definition, okay? A00 plus A11 plus A22 plus all the way to An minus 1, n minus 1, because it's diagonal. So row equals to column. So must be AII, right? So I can write this as the sum of I equal to 0 to n minus 1 AII. Make sense? Then you start counting. A00 plus A11, I equal to 2 plus A22, I equal to 3 plus A33. All the way to I equal to n minus 1 plus an minus 1, n minus 1. Very simple, just sum it up. Okay? And this is very useful in the future. I don't know if we will use in this class, but you should learn. Right? For example, Pauli matrices are traceless. Can you guess what's the meaning of traceless? Huh? Good, thank you. Less means no trace, right? But this is just a number. What do you mean by no? Must be 0 instead of negative or positive, right? So let's try. What is the trace of, let's say, sigma x? It means it's the trace of 0, 1, 1, 0, right? How do you calculate? It is 0 plus 0, right? Only the diagonal. So it is 0. True. What is the trace of sigma y? Just spell it out. 0, negative I, 0. So again, it is 0 plus 0. So it is 0. How about the trace of sigma z? Is trace of 1, 0, 0, negative 1 equal to 1 plus negative 1, which is also 0, right? So it is traceless. That's one property of the Pauli matrices. Okay. And then there are some very important property, right? Given, right, this is a theorem, or I don't know if we call it theorem. If you have two matrices, A times B, A is a matrix, B is a matrix, and A times B is what? A number, vector, or matrix? Still a matrix, right? So I give you this matrix, A times B. The trace is A times B equal to B times A in general. In general. Right? If you remember, we learned about anti-commutative relationship in Pauli matrix. Or is sigma x times sigma y equal to sigma y times sigma x? Maybe you forgot, right? But in general, they are not. Very easy to understand. You rotate me forward by 90 degrees, and then vertically rotate to the other side by 90 degrees. is different from I first rotate vertically by 90 degrees and then rotate forward by 90 degrees. They don't commute the two actions. Right? Or like I standing this operation, I go forward 1, 2, 3, and turn left 1, 2, 3. I stay here, right? But what if? Oh, that doesn't work actually. That is that. I go forward 1, 2, 3, and turn left. That is my final state, right? Another is I turn left and then go forward 1, 2, 3. There are two different states. You see that? They don't commute. Okay? They don't commute means you cannot swap them. So, however, if it is a trace, however, the trace of, if you swap them, the trace is still the same. Okay, this is the probability. Why do I want to say this? Then let's think about what we just learned. The trace of the new representation of U, the operation in the new basis, is equals to the trace of nu is equal to m times UO times m dagger, right? We just proved that. This one. U nu equal to m times UO times m U dagger, right? Now I treat this as two matrices. I call this A, call this B. Then what? Then I say that the trace is still the same if I move B in front of A. This is B and this A. Is that okay? I just use the theory. Trace of AB equal to trace of BA. So trace of M times this whole thing equal to MUO times M dagger equal to M dagger times MUO. But what is M dagger times M? Again, is equal to I, right? Because this is unitary. We assume it is unitary. So this is equal to the trace of UO. Oh, nice. Then it means, or even you observe the operation in different bases. Yeah, you have different matrix form, but they have the same trace. Then you will see that trace is another very important property of matrix, right? Earlier we say the eigenvector are the important property of that matrix, right? Because actually no matter how its eigenvalue is not going to change, no matter how you observe it in different frame. And now you see that the trace is also the same. But actually, if you remember, if you represent a matrix in the eigenbasis of that matrix, it will be diagonal. And all the eigenvalue will appear along the diagonal. And since eigenvalue doesn't change when you change the coordinates, then of course their sum will not change also. And that justifies what we just said. Okay? So you need to think about this, but anyway, important thing here is definitely you should know what is trace, okay? Otherwise you will fail this class. We are not going to test this, but you should know what is trace, right? Sum of the diagonal element. Second is what is traceless matrix. Third is this equation. You are going to use this very often in the future, okay? Might not in this class, but if you continue. Okay, so with this basics, some digression, then let's go back to the quantum gates. Last time we talked about quantum gates, but all those quantum gates has classical counterparts. That means you actually have them in classical logic, like the log gate, right? Again, how we define quantum gate? We define it by say how it changed the basis state, right? NOT gates, phase shift gates, etc. So the first gate we are seeing is truly quantum, right, is the so-called Hadamard gate. Usually just call it Hadamard gate instead of Wash Hadamard gate. So again, the definition, always definition is how we define the quantum gate, right? H, we call it H. Apply to 0. If it's a NOT gate, apply to 0, what do you get? Get 1, right? If it's a phase shift gate, you apply to 0, what do you get? Still 0. I just try to remind you, help you recall how we define a quantum gate. In Hadamard gate, you apply to 0, it give you 1 over square root 0 plus 1. That is a superposition of 0 and 1. Make sense? And by definition, if you apply it to 1, then you give you square root 0 minus 1. And we have a special name for it. For plus, we just call it plus. And for minus, we call it minus. That's just a definition, right? The way we call it. But it turned out that these two are the eigenbases of sigma x. That's it. There's some special properties. And in matrix form, we always need to know its matrix form, because in computer, we use matrix. H equal to 1 over square root 2, 1, 1, 1, negative 1. Okay? You can try to check it, right? For example, what is the Hadamard gate applied to 1? If you use matrix form, this is 1 over square root, 1, 1, 1, negative 1. What's the representation of 1 in column vector? 0, 1. Then we do the multiplication. I try to do it slowly. It becomes 1 times 0 plus 1 times 1, 1 times 0 plus negative 1 times 1. No. What did I say? 1. Oh, yeah, of course, that's right. Then what is that? 1, negative 1, right? And what is 1 negative 1? Just 1 over square root 0. Yeah, you are right. But I try to be very slow. 1, 0 minus 0, 1. Am I right? 1 negative 1 is just 1, 0 minus 0, 1, right? Which is 1 over square root 2, 0 minus 1, right? I just try to check if it is correct. Again, I'm helping you to review, right? We might not have much time for midterm, but all these minor things, you should know it well, right? I mean, in some class, I could have just give you this, and then we are done. But now I will try to go this step by step. Any questions? So that is the Hadamard gate. Now, in Hadamard gate, we take the opportunity to review how to find the inverse of a matrix. And it's because it has some special property. So this has quite some math, right? But which is okay. What is the inverse of a matrix? Let me write it down first. The equation, it is confusing. The inverse, we say, h to the power negative 1, turn out to be 1 over the determinant of h. And then you have a matrix. You need to do transpose. Inside, you have the elements are negative 1, I plus j. And then you have maybe let me don't use capital. You have a number which is called minor ij. Well, very complicated, right? But that is the formal definition of the inverse of any matrix. You can go to any dimension. Turn out to be very easy in 2 dimensions, right? But you see there are a few things. This is the determinant. Okay, which I assume you know that. If not, you need to go back to review. Okay, and we have transpose, right? And we have something called minor. But before that, can you tell me what is the meaning of this bracket again? If a matrix has many numbers, why I only have one number? Look at this is just a one number, a scalar times negative 1 to I plus 1. What is the meaning of this again? The ith row and jth column elements equal to this. That's it. Okay? So you have the first row, the 0th row, first column, then you just plug in I equal to 0, j equal to 1. M will be I equal to 0, j equal to 1. Okay? And then with something called minor. Minor means that you just delete the ith row and delete the jth column. And then find the determinant. Yes. How I get this? So if you want, so everyone, okay, let's digress a little bit. Come back, just this one, okay? So how do you get this? You either guess it or just again go back to, for example, the first element, H11 equals to 1 sandwich expectation value of H, right? You just plug in by this definition, then you will get 1, -1, okay? I showed that in last lecture. You try it. Try it. If you don't know, let me know, okay? Okay, so this is the definition of the inverse. So let me start doing this step by step. First of all, I want to find the determinant of H, okay? So it means that I need to find the determinant of 1 over square root 2, 1, 1, 1, -1. Now, for this one, you need to be very careful. You cannot take out the 1 over square root 2 just due to the definition of determinants, right? You need to multiply this inside. Then it becomes 1 over square root 2, 1 over square root 2, 1 over square root 2, -1 over square root 2. Okay, and how do you find determinants? You multiply this one and then minus the product of the other one, the other diagonal. Right, so what does it mean? It means this is 1 over square root 2 times -1 over square root 2, and then instead of plus, sorry, it should be minus. I say the wrong thing. Minus 1 over square root 2 times 1 over square root 2. So this one gives me -1. Let's pause here. Are you okay with what I'm doing? How I get the determinant? Multiply the elements along the diagonals for 2 by 2, right? And then subtract the product of another diagonal. So that's why 1 over square root 2 times -1 over square root 2 minus 1 over square root 2 times 1 over square root 2. So the determinant of H is -1. Any questions? Right, so you should be able to do this for any 2 by 2 matrix. I won't ask you to do a higher dimensional matrix. Although 2 by 2 can be faster, we don't need to use this equation, but I still want to remind you. Okay, then what is M00? M00 by definition is, again, as I told you, it is the determinant of the matrix, the Hadamard matrix, after you remove the 0th row and 0th column. You delete these 2 rows, it becomes a smaller matrix. If it's n by n matrix, now it becomes n-1 by n-1 matrix. So because it's M00, so I remove the 0th row and 0th column. Then what is the determinant of this guy? Just itself, right? Because it's just a number. So this is -1 over square root 2. Okay? It's not to confuse you. And then, what is M01? Let me do it one more time. This time M01 is 1 over square root 2, 1 over square root 2, 1 over square root 2, -1 over square root 2. But I need to remove the 0th row and 1st column. So what is left? 1 over square root 2, right? And similarly, I want to find M10. Again, it is first I write down the original matrix. And then I will remove the 1st row and 0th column. Okay, and this becomes the minor of this element. So it's 1 over square root 2. Okay, and similarly, M11 equals to 1 over square root 2 1 over square root 2, 1 over square root 2, negative 1 over square root 2. And I should remove the first column, first row and first column. And this gives me the 1 over square root 2, right? Then now I can construct the matrix. So H minus equals to 1 over negative 1 because the determinant of H was found to be negative 1. So 1 over negative 1. Okay? Then I'm going to spell the matrix first. The first element is negative 1 times 0 plus 0 because it's the first row, 0th row, 0th column. I equal to 0, J equal to 0, right? But times M0, 0. What is M0, 0? Negative 1 over square root 2. Okay? And then, how about this one? The second element is what? Negative 1 to the power. What is I? I is 0. What is J? 1, right? And then this is M0, 1, which is 1 over square root 2. So I do the same thing for this. This is 1 plus 0 because it's the first row, 0th column. And then this is 1 over square root 2 because M10 is 1 over square root. This is negative 1 plus 1. Then this is, again, 1 over square root 2. But I need to do a transpose. So based on this, I see that I have negative 1 in front. And inside, whenever I 0 plus 0 or 1 plus 1, then it becomes positive, right? So this is negative 1 over square root 2, negative 1 over square root 2, negative 1 over square root 2, 1 over square root 2, and then transpose. Make sense? Am I right? This one, and to the power 0. So this is only negative 1 over square root 2. This one to the power 1, so it's negative 1 times 1 over square root 2. This one, again, negative 1 times 1 over square root 2. And this one is negative 1 to the power square, so this is positive 1 times 1 over square root 2. So I get this. Anyone have any question or disagree? And then I do transpose. Let me ask you, when you do transpose to this guy, does it change? No, right? Because it's symmetric, right? Across this diagonal. So I'm going to swap these two elements. They are the same. And then I multiply negative 1 to it. What do I get? 1 over square root 2, 1, 1, 1, negative 1. Do you see that? And what is this? Right? We keep doing the math, but then what are we trying to find now? We're trying to find the inverse of Hadamard gate. And turn out it is itself. Okay, so this is a very important thing. Hadamard gate equals to its own inverse. And I actually have this question in one midterm. I put many Hadamard gate and inverse together, H minus, H minus, H minus. And I asked the student to find out what is the matrix of this circuit. So those who study will say that, okay, it is 1. Those who did not did a lot of matrix multiplication in that midterm. And usually they got it wrong. Okay, so I'm not going to torture you in midterm. If you see that you need to do a lot of multiplication, probably you are doing something wrong. Okay, so the main point is H equal to H negative 1. No, I mean H equal to H negative 1. And then I still have not go to the point about that midterm. We are still not there yet. So because of this, then let me just jump right. So this is final. Since H equals to H negative 1, right? Then H, so I say something wrong. Okay? What I said was correct. No, I did not say anything wrong. I multiply h to it, right? To both sides. Something times its inverse is what? Yeah. So what I'm trying to say is h times h is equal to identity matrix. Okay, so in the middle I actually have a circle h. But of course h is also equal to inverse h, so I can do whatever I want. But what I'm trying to prove is that h times h equal to I. Okay? And that's why h times h inverse is also equal to I. Right? No, Hadamard gate is not Hermitian. You see Hermitian? Probably not. Yeah. Oh, you're saying the dagger of h times dagger of h. Oh, yeah, then it is true. Yes. Yeah. Okay, then I'm going to do something more complicated. We are almost done with the simple thing, right? All the linear algebra. Now, from now on, we are going to quantum algorithm very soon. So now we need to work with a lot of math. But I hope that the time I spend with you to go through this, how each qubit changes, have helped you build up the understanding. So let's see what happened. My goal here is that, okay, with 0, right? H applied to 0 with 1 qubit, it becomes 1 over square root to 0 plus 1. What if applied to n qubit? What would it be? That's the question here. Right? And you all can derive it in exam if I don't teach you, because you have the truth already, right? But let's see. First of all, what is the meaning of many qubits, right? So I want to ask psi equals to h tensor product n 0 tensor product n. Now this one you get confused already. Only mentioned this one time during the register when we talk about the 1 qubit has 2 basis state, 2 qubit has 4 basis state, right? So when I say tensor product n, it means I have an n qubit state. Each of them I apply a Hadamard gate to it. I have n of them. And in this n qubit space, I also have the basis states for each of them at 0. Again, I have n of it. Is this okay? And more, maybe I should have done this also. This is also the same as saying, if I really label them, I can call this one, maybe C. I want to make this clear. I can also call maybe, let me call this the 0th space. This is n, but let me don't use this direction because I want to show you 0 and 1. Let me call this 0 space, 1 space, n minus 1. Then this is 0, 1, n minus 1. Basically, this is just saying that apply Hadamard gate in the 0th qubit space, the 0th qubit on this. And then tensor product Hadamard gate in the 2nd electron, for example. And then tensor product all the way to Hadamard gate in the n minus 1 electron. Is this okay? Right? Basically, you have 1 qubit, right? But I have n different spaces, right? I just Hilbert space. I just label them H0, H1. Same for their basis state, I call 0, 0, 0, 1. And so this is a typo, right? Should not be n minus 1. What should this be? 0. Thank you. I'm talking about the basis state of the n minus 1 Hilbert space, right? Or think about I have n electron. So we would have said this, but you should be good enough now. You in your mind, you know, yeah, I know they have n qubits, so of course different n space. So I just arrange them as H0. I even don't label them. I just H tensor product H, tensor product H, I know that this one, this H can only apply to this zero. It cannot be applied to other zero because they live in different universe, different space, different Hilbert space. Okay, so my question now is that I have, and the short form notation is like this. I say tensor product n, it means that I have n of them the same. Okay, so how does it work? So actually I can now then decompose it, right? This becomes H on 0, tensor product H on 0, tensor product all the way to H on 0. But we know that we are talking about n different spaces. Okay? If that is the case, you already know what the result is, right? What is, when you apply the H to 0, what do you get? Hadamard gauge, 1 qubit? Plus, okay, but can you spell out in 0, 1 basis? 1 over square root of 2, 0 plus 1. And we did not label it, but again, you remember this is the 0th Hilbert space, right? Tensor product square root 0 plus 1. Tensor product all the way to 1 over square root 2, 0 plus 1. Correct? And if you kind of forgot or confused, then remember, this is talking about the 0th space, this is the first space, and this is n minus 1. And let me ask you again, how many qubits do we have here? N qubits. Then, a stupid question. Then, if n qubit, why I have 0 plus 1? Isn't that this is 2 qubit or no? Still 1 qubit. It's just the superposition of the basis state, right? So don't get confused, right? This is just plus. Okay. Now, but we already learned how to play with tensor product, right? You just like the regular multiplication we have. So we can use distribution law. But before that, how many 1 over square root 2 do we have? N. So I can write it as, for 1 over square root 2, I can write it as 1 over 2 to the power 1 over 2, right? But now you have n. So this is n over 2. 1 over 2 to the power n over 2. Is that clear? Over 2 because you have square root 2, and then you have n of them, right? So 2 to the power n over 2. So I'm done. And then you need to start multiply them out. Let's first do the first two, right? Okay, you will get how many terms for these two? There are 4 terms, 0, 0, 0, 1, 1, 0, and 1, 1. And they are tensor product, right? 1, 1 means 1 tensor product 1, right? Okay, if that is the case, then we need to keep doing, right? But now let's look at this. So if that is the case, let me do it slowly. I'm going to do 0 times 0 times 0 all the way to times 0. Right, that is one solution. One term. So I have 0, 0 all the way to 0. I have n0. That is one term. Make sense? I omit the tensor product symbol. Otherwise, it should be 0 tensor product 0 tensor product 0. This is all 0, right? Now, if I finish this, just to be systematic, so I don't miss any term, I still multiply everything by 0. Until the last one, I will multiply by 1. We count from 0. 0, 1 to n minus 1. So that's why you have n terms. So I multiply 0, 0, 0, and now I will do 0 for all of them, except in the last one, I will multiply by 1. That is a new term, right? If you don't get it, you can try maybe n equal to 3, play with that. So then I get 0, 0, 0, 1. Again, this is n terms. Right? So I keep doing. What is the next one? It will be 0, it will be 1, 0, right? because I already finished all the permutation of the last term, then this time I'm going to multiply the 1 of the second last term, and then multiply 0. Then 1 of the second last term, multiply 1. And eventually, what do you have? The last one will be 1, right? Because I'm done with all the 0, then we start with 1. So eventually you will get n1, right? And you think about that, this is just the permutation of all these numbers, 0 and 1. And turn out it's just counting binary numbers from 0, all 0 to all 1. Okay? So think about that, and I just want to say, so this is equal to 1 over 2 to the power n divided by 2. If I can make it simple, I just say I have n0, and then 1, and then all the way to 1 or 1. Make sense? But I told you, this is just a notation, right? I can also call this in decimal. 0, 1, 2, 3, all the way to, what is the value of all 1? N bit of 1. What's the value of it? 2 to the power n minus 1. Right? So let me finally write down the result. It is summation k equal to 0 to the power 2 to the power n minus 1, 1 over 2n divided by n divided by 2k. Maybe I should put this one out. Sorry. Equals to 1 over 2 to the power n divided by 2k. So what's the meaning of this based on that? How many basis states do you have for n qubit? 2 to the power n. We discussed it earlier, right? And what are the basis states for 2 to the power n, for n qubit? What are they? What are the value of the basis state? 0, 1, all the way to 2 to the power n minus 1, right? Let's say n equal to 3. The basis state are 0, 1, 2, 3, 4, 5, 6, 7, right? Or 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way to 1, 1, 1. Now, it tells us that if you apply the Hadamard gates to the basis state 0, you will get the sum of each basis state. And what do we call this in quantum mechanics? Huh? It is the sum of the states, not the matrix vector, right? Basis superposition. You know that already, but this is a general superposition, right? 0 plus 1 is a superposition. But more importantly, do they have the same weight? Yeah? What's the probability of measuring one of them? One over 2 to the power n, because it's square, right? So does it make sense? Because how many states do I have? 2 to the power n. The probability of measuring each of them is 1 over 2 to the power n. So you add them together equal to 1. Nice. So this is does not change anything, right? It's still physically correct. So it gives a equal superposition. This is a very important gate. Once you do this equal superposition, you can do entanglement or many different things. So that's why Hadamard gate is so important, right? There are not many gates named after people. Hadamard gate is one of them. Okay? So I will stop here because I finished the material. Any questions?